Students, I am going to discuss about calibration and comparison of venturimeter, orifice meter, water meter and rotometer in this session. This experimental setup contains 4 meters fitted in it. A venturimeter, orifice meter, rotometer, water meter, and a collecting tank is also present here. There is a pump that supplies water from the sump. The supplied water is flowing through this hose and it flows through all the 4 meters before it is getting collected into the collecting tank. This photograph shows the direction of water flowing through all the 4 meters before it is getting collected into the collecting tank. There is a valve fitted at the delivery pipeline of the pump. So we can able to adjust the valve position so that we can able to control the discharge of water flowing through these 4 meters. For a given valve position, the rate of flow of water flowing through all the 4 meters will be same. Now the water which is delivered to the delivery pipeline is flowing like this, and it is flowing downwards, and it is first entering through the rotometer. Then the same water is flowing through the water meter. After flowing through the water meter, it goes along this pipeline. It is flowing through the venturimeter. The venturimeter is connected with a manometer containing mercury. Then the water flows through the orifice meter. This is the orifice meter. Again, the orifice meter is connected with a manometer containing mercury. Then after that, the water is taken to the collecting tank. I will show the direction of water again. It is flowing like this, entering through the rotometer, flowing through the water meter, flowing through the venturimeter, flowing through the orifice meter, and what is collected in the collecting tank. The water first enters the rotometer. The rotometer is shown in the enlarged view. A rotometer contains a transparent container, and there is a scale fitted on the outside of the container, and the float which is moving inside determines give the reading of the discharge. So depending upon the discharge of water flowing through the rotometer, the float level is stabilizes. When the float level stabilizes against a certain reading, the reading is a direct measurement of discharge in LPM, liters per minute. Suppose the float stabilizes against a reading 20. It means that the discharge is 20 liters per minute. So this is how you have to make use of the rotometer for the measurement of discharge of water. Then the water flows through the water meter. Now the water meter is shown here. The water meter, there is a needle. When 10 liters of water flows through the water meter, the needle completes one full revolution. You have to measure the time taken for 10 liters of water to pass through the water meter. So if you know these two values, we can find the discharge. So volume of water is 10 liters. Time, time taken for 10 liters of water to pass through is TW. We can find the discharge of water. Then the water flows through the venturimeter. Venturimeter has got two cross section, main section and the throat section. The area of the main section is A1 and the area of the throat section is A2. Then the water flows through the orifice meter. The orifice meter has orifice, opening, whose area is A2 and the pipe area is A1. After passing through all the 4 meters, the water is getting collected in the collecting tank to find the actual discharge. See, the same water is passing through all the 4 meters when the position of the valve is not changed. But the reading shown by all the 4 meters will not be same because of the accuracy difference between all the 4 meters. A venturimeter may be most accurate. The reading shown by the venturimeter may be very close to the actual reading. So like that, we have to compare the reading shown by each of these 4 meters with the actual reading. So the actual discharge can be measured using the collecting tank. So we have to measure the time taken for certain rise of water level in the collecting tank, and we can measure the actual discharge using the formula AR by TC, where TC is the time taken for or centimeter rise of water level in the collecting tank. The theoretical discharge of the venturimeter can be found using this formula. QV is equal to A1 A2 divided by square root of A1 squared minus A2 squared into square root of rho m by rho minus 1 into 2G HV. So here HV is the level difference of mercury in the manometer which is connected with the venturimeter. So as you can see here, so there is a manometer connected with the venturimeter. So the manometer is filled with mercury. We have to find the level difference of mercury, that is called HV. Similarly, we have to find the level difference of mercury in the manometer fitted with the orifice meter, that we can call as HO. So this formula will give you the theoretical discharge through the venturimeter, where rho m is the density of the mercury and rho is the density of water. HV is the reading shown by the manometer. Similarly, the theoretical discharge through the orifice meter can be found out using the same formula. Okay, now you have to take the reading shown by the manometer attached with the orifice meter, HO. Once you know these two theoretical discharges through the venturimeter and the orifice meter, we can find the coefficient of discharge of venturimeter using this formula. CDV is equal to QV by Q actual. Similarly, the CD value of orifice meter can be found out using this formula, QO by Q actual. Now for the water meter and rotameter, we don't find CD value. We are comparing the reading shown by these 2 meters with the actual reading, and we find the percentage error. So the theoretical discharge through the water meter is given by volume of water collected divided by time. So the water meter, we note the time taken for the needle to complete one revolution. That means 10 liters of water has passed through the water meter, and the time taken for the 10 liters of water is TW. Okay, so volume by time will give you the discharge. So the volume of 10 liters is converted to meter cube, 0.01. The theoretical discharge through the rotameter can be directly found out. Since the reading shown by the rotameter is in LPM, liters per minute, we have to divide with 1060 to convert into meter cube per second. So once we know the theoretical discharge through the water meter and the rotameter, we can compare this with the actual discharge to find out the percentage error in water meter reading and rotameter reading. So this is the formula to be used to find the percentage error in the reading shown by the water meter, Q actual by minus Q W divided by Q actual into 100, where QW is the reading shown by the water meter. Similarly, the percentage error in the reading shown by the rotameter can be found using this formula, Q actual minus Q rotameter reading divided by Q actual into 100. So QR is the theoretical discharge shown by the rotameter. So once the experimentation completed, we can draw the graph. So by changing the valve position, we can able to find the reading for different discharge level. Then we can draw a graph between actual discharge and the CD value for the venturi meter and R phase meter, and for the water meter and rotometer we can draw another graph, okay, between actual discharge and percentage error.